In this slide, we will talk about floating point representations, which represent the fractional numbers or quantities. In the previous slide, we talked about integers, which doesn't have fractional or decimals. Now, of course, we will have decimals in the numbers, as you can see here. After the point, we will have some values. Then the representation of integers will not work for this case because it only shows integers. Instead, we will use a floating point representation. And in the floating point representation, simply we will have three symbols or three terms, m times b to the power e. And here, m is the fractional part. This is also called mantissa or significant with a D. In general, we will call this as mantissa. And we will have the base. B is the base, actually. And we already know this. For a base 10 system, it is 10. Base 2 system, for base 2 system, is 2. Base of the number system. Also, E. E is an integer. And it is the exponent which makes the fractional part as our number, actually, by multiplying. We will show this example a few moments later. Integer called exponent, or it is also called characteristic. Let's say or. So let's look at this example fractional quantity 156.78. We know that this is base 10 first of all. Let's write it in blue. This is base 10. Just our current number demonstration system. Base 10. Then B is 10. So we will find this M and E as well. And let's say mantissa, which is M. And we will define M always with decimals. And it will just after the point. So point something, 0 point something, let's say. Here we will make the entire number as 0.15678. We need to do that to define mantissa. It is just a fractional part. So it only shows the decimals. And that means M is 0.15678. And if we represent the M like this, to be able to move the point from here to here, we will have 3 actually 10 multiplication, or we will multiply this by 1000, which gives us b to the power 3 actually. If e is 3, we will have here 1000 and multiply it by this, it will give us 156.78. So the exponent then is E3. By finding these, we can simply write m times b to the power e is equivalent to 0.15678 times 10 to the power 3. And this is it. We defined a fractional quantity with floating number demonstration. This is the floating number or representation. And in computers, in a word, you can see here, a floating number can be stored with this notation. And we will have the sign again in the first digit. And also we will have a sign for this exponent here. And then we will have the mantissa. Or actually in the signed exponent, we will have a sign initially. Let's draw like this. A sign for exponent. Then the exponent here. If it is 3, for example, it will define here. and this is if this is positive, this is just 0, for instance. And we will have the mantissa here with the representation of this. So we can have an example of this in the following slide. Before having an example of the computer representation of a floating point, let's talk about the normalization concept of a floating point, because we have this concept especially when we have leading 0 digits. In other words, in the previous example, for example, it started with integers, but here we will have leading 0, so the number is 0.02. And what are we gonna do if we have this? Because we want to have 1 0, then the numbers should start. So we can use a normalization approach to be able to represent this with the floating point. How are we gonna do this? Let's define here. So for a base 10 system, which allows only 4 decimals, let's give an example of this, and m will be only 4 decimals, which means after point the decimals will be 0 2 9 4. So we are not able to write the whole numbers, all of the numbers. We can only write 3 of them, as you can see, because with 1 0 1 2 3 4 decimals we can store only. In this case, we will have e is 0, and of course base is 10, and with this we can represent this number as only 0.0294 times 10 to the power 0. If it is 4 decimals, it can be stored. But the problem here is that this is e actually. Let me do this way. This will be e. Because e is 0, this is a problem for the computer, because we have a useless 0 and we skip one number here. We can maximize our representation by simply, if we can remove this 0, we can maximize the representation of the numbers. And to do that, we don't want e is 0. We can make it 1 and have a better representation of this number. So that's why we use normalization. We normalize it to remove the leading 0 by multiplying the m by 10 and lowering e by 1. So we will just make e is 1 and simply minus 1 actually, and simply we will have this results. So in other words, here we can have m is, so m has to be after point numbers 2 9 4. We can have the additional 1 now, and then e will be minus 1 and b is 10. In this case, the number is shown by 0.2941 times 10 to minus 1, power minus 1. As you can see, with the demonstration of this, we maximized our representation of a number. And this normalization gives us actually range for the m values. You can see here at the bottom, with 1 divided by b, and m should be greater than that and should be smaller than 1. If we give an example of base 10 system, we have 1 divided by 10 smaller than equal m and smaller than 1. So m can be as minimum as 0.1 and can be as large as 1 but not equals to 1. And for base 2 system, similarly, we will divide just 1 by 2, m again 1. So it is between 0.5 and 1 this time. So let's have an example to show this. as well as show the floating point representation on a computer in the following slides.